Hi folks, I'm John Grant. I work here at the National Air and Space Museum up in the Center for Earth and Planetary Studies. I'd like to welcome you to What's New in Aerospace. Today I'm going to be talking about recent results from the Mars rovers and looking ahead a little bit to think about what we might be doing next on Mars to try to understand the history of the planet and whether there might have ever been life there. So could I go to the first slide, please? Could we get the graphics up? There we go. I changed the title a little bit here. I was originally asked to talk about the mission to Mars, but I'm going to talk about missions because it turns out in the scale of my lifetime anyway, there's been a lot happening on Mars. There's been a lot of results from a number of different missions, and they're all building towards sort of a seminal question about whether or not there was ever life on Mars. That's something we kind of want to know and understand whether life is unique to the Earth or whether it's something that we might find elsewhere in our own solar system. To do that, there's been a fairly systematic approach to understanding the kinds of environments that have existed on Mars in the past. And we've used both orbiting spacecraft as well as landed spacecraft like the rovers that you see here to try to get at the questions that tell us whether the conditions were ever right for life and eventually whether or not there was ever life on Mars, and of course ultimately whether humans are going to get to Mars and what they will do when they get there. So here are a couple of pictures of rovers that are currently operating on Mars. On the left, we've got the Opportunity rover. And I want to point out that Opportunity is actually one of a set of twin sisters, if you will, of rovers that were launched and landed back on Mars in 2004. So for Opportunity, the anniversary, the 12th anniversary for the rover, is coming up in just a few days. It's on January 23rd. So a rover that has been going on Mars for 12 years is something in and of its own right. But that rover was designed to last only 3 months. So we're talking about something that has far exceeded expectations in terms of its operation, but also far exceeded expectations in terms of exploration and discoveries. On the right is sort of the big sister, if you will, but also the younger sister. This is Curiosity. It landed on Mars back in 2012. And whereas Opportunity is about the size of a golf cart, Curiosity is much larger. It carries a larger science payload, number of instruments, and it's about the size of a Mini Cooper. So two different vehicles, two different lifetimes, and they're in two different places on Mars, exploring different kinds of habitats. Okay, and I did not get the slide to go forward. So if we could you guys advance the slides? There we go. What I'm showing you here is a map of Mars. It has polar caps that you see here. And Mars is an interesting place because it's got a lot of landforms that in many ways are quite similar to those that we see on the Earth. There's volcanoes, there's large canyons, and it also turns out that there's valleys that for all intents and purposes appear that they've been carved by running water. We've landed on Mars a number of times, and the yellow names that you see up here are all landing sites, starting back with Viking 1 and Viking 2 in the 70s and coming forward all the way to Curiosity. Opportunity and Spirit you see there near the equator. Opportunity sort of in the dead center of the image, and Spirit over there to the right. And I'll talk a little bit about their landing sites in a moment and the kinds of discoveries that they've been making. Curiosity is sort of between the two, and a question that I get a lot of time are the rovers ever going to drive over and see each other? And I want to give you a sense of scale that while Mars is smaller than the Earth, about 40% the mass of the Earth, the surface area, the land that you see there on the surface, is about the same as the land area above sea level on the Earth. So that's a lot of territory to cover. And even though you see sort of a handful of spots where we've landed, it really doesn't describe fully the diversity of landforms and features that we see on the surface of Mars. So no, the rovers are never going to go over and see each other because they're far, far apart. Okay, this is not working, so could I go to the next slide, please? Here is sort of a graphic of the rover Spirit and Opportunity on the surface. And the way that I like to think of them as a team member is that these are robotic field geologists. They're kind of like the equivalent of me with a rock hammer and a hand lens going out onto the surface and banging on the rocks and trying to understand what created those rocks, what environments they were formed in. The role of the rovers is to try to understand the role of the geology of the surface and the role of water in shaping the surface of Mars. One of the reasons for that is, as I mentioned, we see features on the surface that were carved by running water. We want to know how widespread that was, how long-lived it was. But the other reason that we want to know something about water on Mars is because it's probably related to life. Everywhere we see water on the Earth, we see life. And we want to know if that kind of hypothesis or connection holds true on Mars and understand where we might use water as a tool for looking for and understanding life on the planet. Could we go to the next slide, please? So here's the landing site of Spirit rover in Gusev Crater. This was formed by a very large meteorite impact into the surface. It's about 100 miles across or 150 kilometers across. And what you see in the bottom portion of this slide, sort of in the middle, is a very large channel that enters the crater. And the idea here is that that channel carrying running water drained into the crater a bunch of water and sediment. And if you look closely at the top portion of the slide, you'll notice that the wall of crater appears to be kind of buried. And so the idea going in was there's this river flowing in, the sediment filled in the crater, and that we could land there and study sediments deposited in a lake. And those turn out to be very interesting for geologists because they're fine-grained and they tend to record by preserving very small-scale features in the geologic record. So we wanted to go there to try to understand whether there was an ancient lake on Gusev and what those conditions were like. Could I go to the next slide, please? When we landed, we actually found something a little bit different. We found a lava plain, and we found out that some of the material that was filling in the crater is actually basalt, much like you would find flowing out of a volcano in Hawaii. And so instead of finding lake sediments, what we found were lavas and basalts and other kinds of rocky material that really isn't the kind of stuff that you want to go to understand the history of water on Mars. Lava comes out at well over 1,000 degrees. It's not something that life wants to go and live in, so why do we want to go and really look at lavas? What we ended up doing instead was heading over to those hills that you see there, the Columbia Hills on the horizon. Because those hills, we could tell from orbit, poke up beneath those lavas, and give us a sense of the older materials that maybe were related to an ancient lake. Now I want to pause for a minute here and say something about the words that you see on this slide. You'll notice that it says approximate true color. And the reason why it says that is because the camera that was used to take this takes an image in several different wavelengths, up to 13, of light. It doesn't see the full range of wavelengths that, for example, our eyes do in the visible wavelength. And in fact, in the case of the camera used to take this, it sees some wavelengths beyond what we can see. So when we want to restore the actual color of the surface, we have to take a few of these slices of the wavelengths used and sort of piece them together. Think of it this way. If I tell you 2, 4, and 6, and I ask you what probably comes in between, okay, you would say 3 and 5, right? 2, 3, 4, 5, 6. But you don't know that for sure. And so in this case, if we say 2, 4, and 6, we're kind of inferring what comes in between. And so it's an approximate true color based on those filters. And you'll see that throughout the rest of this presentation. Now, in some cases, we use what's called false color. False color emphasizes in a portrayal of an image certain filters, certain kinds of wavelengths, because different kinds of rocks sort of express themselves better in those wavelengths. So you'll also see some examples of things called false color, and I'll tell you about those as we go through them. So after we landed, we saw this basalt plain, and we headed over to the Columbia Hills because we want to understand whether there was a lake in Gusev Crater. Could I get to the next slide, please? So here's our trek. We started over here in the top left. We headed up to a crater called Bonneville. The initial purpose behind that was to try to understand whether or not the crater itself, which was formed by another meteorite, might have created a hole that punched through the lava and exposed the lake sediments. The answer was no. So off to the Columbia Hills we went, down there in the lower right, and you can sort of see the zigzag switchback pattern that we made as we climbed up. Spirit became sort of the first mountain climber on another planet. And I want to point out a couple of things here. Comanche that you see sort of in the lower right is an area where we found an outcrop that was quite interesting, and then down at Home Plate. I'll talk very briefly about some of the discoveries that we saw in those two places. So right in the upper sort of center of this slide, you see a reddish looking rock sticking up. That's Comanche. It's about 5 meters across from the far right to the far left. And it turns out that that rock, when we look with our instruments on board Spirit, has something called carbonate in it. Now, carbonate is not so important for you to understand in terms of its absolute composition. for the purposes of this, it's very interesting because carbonate exists where it's not too acidic, not too basic. The water's just kind of just right. It's the kind of water that we drink. It's the kind of water that we swim in. It's the kind of water that life exists in. Okay, so it turns out that carbonates, this is the first discovery and measurement of carbonates on the surface of Mars, become a very important sort of clue as to what ancient conditions were like on Mars. It turns out that in some times in the past, at least here in Gusev Crater, the water that was there was the kind of water that we would say is good, is habitable, in the sense that life could have existed. A little bit further to the south, the Comanche outcrop was just above the slide here to the sort of center right, is this feature called home plate. And home plate is about 60 meters across, so a little less than a football field, if you will. And you can see even at this scale from orbit that there's layers here. Now I want to say a little bit about this image, and I should have mentioned something about the previous image, that this is taken from orbit by a spacecraft called the Mars Reconnaissance Orbiter. And the camera on board, called HiRISE, looks down on the surface and can actually image things with a scale of about a foot. So if we peeled off the roof of the museum and looked down at each person in here, we'd see a spot corresponding to the top of your head. My spot would obviously be a lot brighter than your spots because I don't have any hair and you guys do. Okay? It wouldn't be able to tell you what color your eyes are or what kind of, the shape of your nose or anything like that. It can't actually tell you that kind of information until you combine a few of these things called pictures or picture elements together. So we can see things on the surface of Mars and tell what they are that are no bigger than, say, the top of a small table. With that camera, in fact, we can see the Spirit rover sitting right there on the northern edge of this. Remember, that's about the size of a golf cart. So we can get down and dirty here in terms of looking through the orbital images and say something about the geology, guiding the rover to the places that we think are the most interesting. And when we did that, we drove up to that northern slope of home plate and we looked at these layered rocks that you see here. Now, the layers are actually flat-lying. It's because the rover drove up onto the side of this thing and then turned this way and then turned that way with its camera, and that gives it the curved appearance. And one of the things that you see here are these layers go from sort of thicker and coarser to finer as you move up through the rocks. And I'm going to point out in the next slide an area just down here where if we look at those layers, you see sort of a U-shaped feature and a rock sitting in it. And this is something that we see a lot out in Hawaii. It's something called a bomb sag, and it's when a rock gets thrown out of a volcano and it lands in the sort of muddy ash that's also been coming out of the volcano and settling into water, and it bends the bed, kind of like you taking your foot and stomping in the mud. And then additional ash comes out and fills in over the top of that. From this kind of feature, we know that when this occurred, there was water here and a volcanic field. So it was hot, locally warm, and also wet. Around the outside of this, we also made a discovery that was quite interesting. You see the bright material here. This is the track from the Spirit rover, and it's where we dragged one of the wheels along and scraped away the sort of dusty surface and found this bright material underneath. It's called silica, and it's something that you oftentimes see out in places like, for example, Yellowstone National Park, or again in Hawaii, where steam is associated with volcanic eruptions and it's depositing material around the outside. It's a fumarole. It's a steam vent. And so in the case of home plate, we've got a volcanic eruption that's happening with water. We've got steam coming out. And we've got a place where we know nearby the water was actually relatively copacetic in terms of being conditions right for life. So it paints a picture of an ancient Gusev crater, probably 3.5 or maybe even 4 billion years ago, that was wet, that was habitable, and that may have been a place where conditions were right for life. So that's sort of a summary, if you will, in a thumbnail sketch of what happened with the Spirit rover. Now, Spirit stopped operating in 2010. And so the next chapter of the story is jumping around to the other side of the planet and talking a little bit about Opportunity. Now, the Opportunity rover actually went to a completely different kind of place. This is a view on the left of a big chunk of Mars, sort of near the equator, running right about through the lower third of that image on the left. And painted on top of it is the abundance of a mineral called hematite. The more hematite there is, the redder this color is. So where it's red, there's a lot. Where there's green, there's some. Where there's blue, there's not much at all. And hematite, it turns out, some of you may have jewelry that's made out of hematite, is a mineral that often forms in the presence of water. So unlike Gusev Crater, where we went hoping to find evidence of a past lake, in the case of opportunity, we wanted to go and find out what this hematite was and why it was there. On the picture on the right shows you sort of what the detailed surface looks like. So on the left, you can notice there's a scale bar down there, 50 kilometers, that's about 40 miles. That's a huge area that's covered by that image. But the image on the right is only about 6 kilometers or 4 miles across. So we've really zoomed in on a portion here, and what I want to point out is just how flat this surface is. You see a very small impact crater there. That's about 7 football fields across. But otherwise, there's not a feature to be found. It makes this stage actually look like a fairly rough surface. So we went to a very different place when we went to Meridiani Planum, which is what this location is called. Now, when we landed, the top portion there is a blow-up. I'm sorry, the bottom portion is a blow-up of a portion there to the upper right. We saw in the small crater a ledge of material which even from our vantage point of where we sat on the lander, we could see was landed. And when we rolled off the lander and we got up close, we found a number of interesting features. Once, these layers that we see are actually punctuated in places by little round balls. They're about the size of BBs, but they're not made out of brass like a BB. They're actually made out of hematite. And you can see an example in the lower left there from the Earth, Moki marbles, as they're called, where we see similar sorts of features. These are formed when water is percolating through rocks, and it deposits the mineral that's dissolved in the water and leaves behind something called a concretion. So the balls that you see in here are actually hematite that were emplaced when in fact there was a lot of groundwater here and the ground was sort of steeped in water. Very different kind of place than we see on Mars today. In other locations, we see these sort of smiles or the little curlicues that you see in the upper and lower portions of this picture. Those are called ripples. And when you go to the beach in the summertime or when you go to a river and you see where the water's flowing, it creates these small ripples that move along the surface. These are the same things formed on Mars. Well, wait a minute. If there's ripples and they formed in water, then that means there was standing water in Meridiani Planum on Mars. We've also got evidence of a lot of groundwater. We want to understand, based on this evidence, how much of the rocks that we see in Meridiani Planum actually relate to these conditions when there was standing water. And so what we did is we headed off into the landscape here. This shows you just how flat the surface really is. Again, an approximate true color. You can see the tracks of the rover are a little more than a meter apart. And we headed off into the landscape towards a large crater that I showed you, I think, in the previous slide, called Victoria. This is about 7 football fields, 700 meters across. You can see where we landed in the upper left and traversed down to Victoria Crater. And the idea of going there was, if you've got a hole in the ground and you can see the rocks exposed in the wall, you can see how they vary and get some handle on how much of those rocks were related to running water and how much was related to some other process. So off we went to Victoria Crater. This is a view, again, from that orbiter, a high-rise image. I discussed the image resolution before. And just to point out, there is the Opportunity rover sitting in the middle of that red circle there on the rim of the crater. And what we did is we sort of drove around this northwest portion here and eventually came back and went inside the crater. And when we went inside, we found something that was kind of surprising. Here's a view of the wall. And it turns out that the rocks that we found that related to past water on the surface, that related to the past occurrence of standing water, are really confined to a fairly narrow band of rocks. The bulk of what you see there are actually rocks that were deposited by ancient sand dunes. And so when we take the evidence that we found in Meridiani Planum together, and we assemble sort of a story for what the geologic record is like in Meridiani Planum, we come up with something that's kind of like what you might find in Saudi Arabia. Now, Saudi Arabia is in the Middle East. It's a desert country. By and large, it's fairly dry. And so when we talk about a place like that, we're not talking about a place that's sort of tropical rainforest-esque. So yes, there is water there, but it wasn't water that was there a lot. And in fact, when we look at the chemistry of the rocks that we see, those rocks were not the kinds of things that we saw in Gusev that were carbonates. They were rocks that formed in places where the water was kind of acidic, where life could have sustained itself, but perhaps was not as ideal a condition as we might have seen in other places on Mars. So a good analogy for this might be a place in Saudi Arabia where by and large it's a very dry kind of environment, but every once in a while it does rain. When it rains, the water sort of pools up between the sand dunes. It evaporates. As the water percolates down through the surface, it deposits the hematite that we saw. But by and large, it's a place where there's sand dunes and sand blowing around. Again, not the kind of place that you think about in terms of abundant water and abundant life. So that's sort of the story of the first part of the Opportunity mission, understanding the role of water in contributing to the formation of these hematite spheres that we saw and how long-lived that water was. The other part of the story relates to how long this mission's been going on. As I pointed out, we're approaching a major anniversary here in just a few days. There's a large crater called Endeavour that's about 22 kilometers across, 16, 17 miles across, that's far away from Victoria Crater, where we were just discussing here. And it turns out that now that we've had sort of a sense of, gosh, this rover may last for a while, let's head on down and check out Endeavour Crater. Because Endeavour Crater, in this the view from the context camera on board the Mars Reconnaissance Orbiter, shows us that the rim of the crater pokes up through those rocks that I've been talking about till now. So the rocks in Meridiani Planum that are kind of like, an analogy of the environment in Saudi Arabia, now we're talking about rocks that are much older, that are buried by those rocks. And if we can get to these, we can look further back in time and get a sense of what this place was like maybe 3.5, 4 billion years ago. So we did a very long trek across the landscape and arrived at the rim of Endeavour Crater. And we spent, the last 3+ years driving along these rim segments here. This is a blow up on the right of the sort of center portion of the rim here, from a place called Cape York down here to Marathon Valley. And I'll show you a little bit about what that's told us about the conditions on Mars. First of all, we see two kinds of rocks, at least on the northern end of this. We haven't seen two kinds yet on the south. We see something called the Shoemaker Formation, that is the busted up remnants, the fragments of the rocks that were there when the crater was formed, when the meteorite hit the surface and created the hole. Underneath that, we see something we've called the Matiovic Formation, and those are the rocks that were there that the meteorite hit into. So these are what we call the country rocks, and this is the ejecta from the crater. And what's very interesting about this is down here in the Matiovic, we see clays. And those clays are another signal of conditions that are sort of not too acidic, not too basic, but just about right for life on Mars. And so we're very interested in understanding what kinds of clays are here, how long they were, and how much there is. So off we drive across the landscape. Again, an approximate true color view here. This is an area called Davion Ridge, and it gives you a sense of the sort of rolling hills landscape of the rim of Endeavour Crater. As we've gone further, we've gotten more recently to a place called the Spirit of St. Louis Crater, which you can see here in the central portion of the slide, and there's this spire that sticks up. We're not really sure exactly whether this is a volcanic feature or a deeply eroded impact feature, but it gives a sense again of the kind of variability that we see in this landscape. And then finally, most recently, we continue to be in a place called Marathon Valley. We're sort of over here in the right-hand portion of the slide, or just out of the view to the right. And this is a place where we see even more clays. And we're still exploring the nature of these clays to understand something about ancient conditions. But we do know that what they tell us is that this is a place where early on in the history of Mars, again, maybe 3.5, 4 billion years ago, the surface was very different than it is today. It had to have been for those clays to be there. It was a place where it was wetter. It was a place where the conditions were much more Earth-like in the sense that the water was relatively neutral. I don't mean to say Earth-like in the sense that there were plants and animals. We don't know that. Well, there certainly weren't big plants and animals. But in this case, we do know that it was at least sometimes wet, and that wet water was occurring in a fairly neutral environment. So we continue to explore here in Marathon Valley and try to piece together this history of Mars that tells us and ultimately something about habitability and whether the conditions that we see that might have been right for life actually might relate to the past occurrence of life on the planet. Okay, so that's the Spirit and Opportunity missions. Now let's flash forward to 2012. Here comes the younger, bigger sister, Curiosity, that I described before. You can see the payload of instruments here that I won't describe in any detail. I invite you to go online and take a look at what each one of these things do, but they're all geared towards assembling a package of information that tell us something about the past habitability of Mars. We went to a place called Gusev Crater, again formed by a large meteorite impact, again on order of about 100 miles across or so. And what drew us to this crater, if you look in the lower right here, is this mountain of material, almost 3 miles high in the center of the crater that we can see even at this scale is layered. And if you zoom in on the upper left here, on this portion of the crater, you can see that those layers tell us something about the occurrence of clays, which I've already described from Meridiani Planum and the Opportunity rover, and other kinds of younger strata that are called sulfates, which are much like the younger rocks that we see in Meridiani Planum. And the conditions that deposited these must have ranged from something that was relatively neutral water conditions to more acidic water conditions. Why is that important? Because it tells us something about the drying of Mars. If it really was wetter and more habitable in the early history of the planet, how did it get to be the way it is today, which is dry and inhospitable? Well, it looks like the layers in this mountain record that story, and so that's why we went there to study it. Once we got on the ground, you can see the names that we've assigned to the rocks. You can see a place called Hematite Ridge, Clay Unit, and Sulfate Unit. Those are those layers that I showed you in the previous image that were taken from orbit, now showing you that perspective from the surface and how we're going to drive across and sample them. Now, an interesting aspect of our studies in Gale Crater with Curiosity is after telling you that we went there to look at the layers in this mountain, in fact, the first thing that we did when we landed was go in the opposite direction. In this slide, the mountain's actually down to the lower left, and what we did after landing here at Bradbury Landing is drive over here to a place called Yellowknife Bay. And I think you can see that there are different colors there. There's a cratered unit that's relatively dark and smooth. There's a brighter fractured unit, and then this hummocky unit that's sort of a brownish that occupies the lower left, the left-hand portion of the slide. At the junction of those, we saw some interesting features that we wanted to drive over and explore. Right away, we started seeing interesting things. The pictures that you see here are of gravels that are formed on the surface. For those of you that walk on sidewalks like I do, every once in a while where a tree is growing, it's bent up the rocks and broken the concrete, and it looks kind of like that slide on the left, that picture on the left. In other places, you can see that there's more sandy material, but still some gravels mixed in. And when we look at the shape of these grains, they're rounded. It tells us something about how they were deposited. And the best analogy we have for this is that this was gravel and sediment deposited when a river flowed down from the wall of Gale Crater and deposited these in a fan of material. If you've ever been out west in a place called Death Valley or other similar kinds of places, you can see where as water rushes out of the steep mountains, it deposits a fan of material and sediment down at the base. This is a very equivalent kind of place, or sediment. But in fact, what's interesting about this is if you look at the size of the gravel, you can say something about how fast the water must have been moving, how deep it must have been. And so we're looking at a place, of course, today, which is very dry, very cold, very inhospitable. But in the past, when these gravels were being deposited, there's probably water a couple feet deep, occasionally flowing down slope and depositing these sediments. So a very different place than we see today. The next piece of the puzzle is we got closer to that junction between these units in a place called Yellowknife Bay, or something called mudstones, where you can see in this selfie that Curiosity took kind of form the bottom of this depression that's been etched out by the wind. Now I want to take a second here and point out that the box on the upper left, and that you'll see in a number of these other images, says something about what these images show you. In this case, the scene is a little bit different than what I showed you from Opportunity and Spirit, where I said it was approximate true color. In this case, because it's a different camera that takes pictures using different wavelengths of light, the way we adjust things to get things to look the way we would think they would look on Earth is a little bit different. And so in this case, when we do that, you'll see a couple of instances where the sky looks blue, and that's not the case. There's not a lot of blue on Mars. It's a red, rusty planet. And so to make things look the way they would to us, to our human eyes, in fact, we have to stretch things a little bit. And so we get something that looks like it would on the Earth in some regards, but in other ways it looks a little different. Okay? Well, when we drilled into these rocks, we found out something that was pretty interesting. A bunch of circles. What in the world is a bunch of circles? Well, this is data taken by the ChemIn instrument on board the spacecraft. And what we did is we drilled into the rocks, and we took some of the drill sediment or grains, and we dumped them into this instrument. And it's what they call an X-ray diffraction instrument. What does that do? Well, have you ever looked at the sun? Don't look directly at the sun. Or the moon. For example, last night, as clouds were coming in aloft, you see a ring around it? Okay, sometimes they call those sundogs, where you see them off the spots. That's diffraction. That's when little particles will actually sort of bend the wavelengths of light. Well, what we did in this case is we took the sediment from the drill and we shined X-rays through it, which is a form of light, just very short wavelength, and the grains of material in the sediment bend that light different amounts depending on what the material is. So the rings that you see here actually change in intensity and position with the kind of material that the light's being shined through. In this case, on the left, what you see is a pattern that's very characteristic of the kinds of minerals that you find in lavas. The Hawaiian Islands are made of a rock type called basalt. This is a basalt, this rock-gneiss sandstone material. On the right is the stuff from the drill core in Yellowknife Bay. And there's a difference if you look down there in the middle portion, right near the black center, where there's a bunch of fuzzy stuff around the outside. And that's labeled phyllosilicate. Phyllosilicate's clay. There's clays there. There's a lot of clays there. I've been harping on clays. Clays tell you the conditions were relatively neutral again, and they might have been habitable for life. Well, in this case, it's a little different than Meridiani Planum and Gusev Crater. In this case, where we see these clays, they're actually occurring in a very fine-grained sediment, mud. When you dry up mud, you get mudstone. And so in this case, where we see these clays, we've got tremendous evidence that there was actually a lake there. We saw the gravels from the river draining down the wall of the crater, and now we see where that water ended up near the bottom of the crater, forming a lake that flooded the floor. When we look with another instrument called the SAM instrument, Sample Analysis at Mars, what this does is it takes our sediment and heats it up, basically burns it. And what we look at as it's doing that is different compounds come off at different temperatures. And the squiggly lines that you see here, one of them shows where water came off at quite a high temperature. And we know that the temperature that that water came off corresponds to a particular kind of clays called smectites. Again, telling us that this was a place in the past that was very different than we see today, where rivers were flowing down the walls of the crater and where there was a lake, at least temporarily, on the floor. Well, we landed up here. That was Bradbury Landing, and we drove over to Yellowknife Bay, which is what I've just been talking about. And then finally, let's head on down to the mountain there. And the yellow star that you see is about where we are right now in a place called the Bagnall Dunes and the Namib Dune Sand Dune, and I'll show you that in just a moment. And during this trek through Darwin, through Cooperstown, through Kimberley, Pahrump Hills, and Marias Pass and Bridger Basin, we've been looking at the rocks to try to find out, just like we did at Meridiani Planum, how representative are the rocks that we saw at Yellowknife Bay for all the rocks that we see across the floor of Gale Crater. Because if they are representative, if we see those kinds of rocks everywhere, that was a big lake, and it was there a long time. And if you're thinking about habitability, places where life could live, a big lake, hey, that's a pretty good place to go. So here we go on our trek down to the south and west, and we see layer after layer of rocks. And if you look at these, you can see that they're actually tilted a little bit, sort of down into the upper left. And the reason that those are tilted is because this is sort of the edge between where those gravels and sands were washing down the wall of the crater and where they entered the lake. This is a delta. These are layers of sediment that build out one after the other as the sediment is deposited into the water at the edge of the lake. And as we go even further, we can see this very, very fine-grained sediment, kind of like the mudstones that I talked about at Yellowknife Bay, in this case in a very different location and potentially a little bit different in terms of their sedimentology. But nonetheless, the kinds of things that you expect to see deposited on the floor of an ancient lake. And so collectively, this tells us something that Gusev Crater, which is again about 100 miles across, must have once had a very large lake in the floor, a very large standing body of water. And in fact, if you look at the bottom portion of this image, on the left-hand side, it shows you that the water may have come and gone. That at sometimes when it was wetter, the lake may have extended across more of the floor. When it was drier, those sediments from the wall of the crater might have built out further. But nonetheless, as that sequence built up through time, it made this stack of sediment that we've been exploring that tells us that this lake has been there. After the lake went away, those sediments have been eroded, and now we've got this mountain in the middle of the crater that at least the bottom portion of which is related to these wetter conditions that I've been describing. So Gusev Crater was a very, very different place, much more habitable in the sense of the way we think about conditions than what we have on Mars today. Now, since leaving the locations that I've been describing and heading further towards the mountainside, we've been traversing through some fairly stunning scenery. This is a place called Marias Pass. And you can see the kind of layered rocks here that transition from those mudstones, those finer grained sediments on the bottom, into coarser grain, which are potentially either water-lane or wind-blown sediments on top. Most recently, and in fact, where we are today, is a place called Namib Dune at the Bagnol Dunes. And you can see the sand dune here behind the rover. This was taken just last month, and in fact, as we speak, the rover is sort of to the left-hand side of this image, scooping away into the sediment and analyzing the sediment to understand the minerals that are present and how wind processes on Mars actually behave similar to or different from what we see as wind processes here on the Earth. So this is a very current image and tells us something about the conditions on Mars today relative to the much wetter conditions that persisted at some time in the past. Well, we haven't lost sight on the grand prize, that 3-mile high stack of sediment that we've been exploring the bottom of actually extends up before us. To me, this is sort of reminiscent of driving across the sort of Midwestern plains as you leave western Kansas and go into eastern Colorado. You're driving, and then finally you see this sort of faint smudge on the horizon, and as you get closer, it's the Front Range of the Rockies. Now, this is a very different setting than what you would see on the Earth in the Rocky Mountains, but nonetheless, to me, it's reminiscent of that sort of looming mountainous landscape in front of us. And it's just beckoning us to come and look at the rest of the layers that make up this mountain, because we've already seen from the bottom portion what we represent an ancient environment of a lake on the floor of the crater. What does the rest of this hold in terms of the history of Martian environments and whether or not the planet was habitable for a very long period of time? So we look forward in the coming months and years to exploring further up into this mountainous range and understanding more about the conditions that persisted on Mars. Now that's kind of what's been going on. Each panel that you see here is representative of a mission, not necessarily flown just by the Earth. You'll see some in the middle there. You'll see EXM towards the right, that's ExoMars, and TGO just to the left of that. Those are European missions. We're not the only country that's exploring Mars, and that's a good thing. What you see here, though, in this package and underneath it are sort of the goals of Mars exploration and how all these missions come together. They're trying to sort of build on one another to understand something about the conditions on life of habitability on Mars and whether or not there was ever life on the planet. And so when we look towards future missions, specifically to 2020, okay, just a few years from now, the next rover is going to take the next step. It's going to try to look for things that we call biosignatures, actually look for evidence of past life on the planet. So I want to talk just a minute or two about that mission, because we've already selected the instruments. This is what you see here. It's got a payload that's very robust, sort of a next generation, if you will, from what's on Curiosity. But when you look at the rover itself, even though this is sort of an artist drawing, you'll probably see some similarities to Curiosity. And that's because it's basically the same rover. We've taken the same rover, the same landing system, but we've put different instruments on it, and we're probably going to go to a different place. And then make that next step to look towards the answer of whether or not there was ever life on Mars. Now, here are the goals of the 2020 mission. I tried to find a spiffy slide on the NASA website, but I couldn't. So I took the words that you see here. And again, it's to seek signs of past life. It's to look at a geologically diverse landing site and say something about the geologic history. We want to look at ancient habitability, make a coordinated set of scientific measurements that allow us to get answers to these questions, but also make a big step towards eventual human exploration. That's something that's very different. And then finally, in smaller text there towards the bottom, we're actually going to collect samples and leave them behind. It's called caching, so that a future spacecraft could go and pick those up and bring them back to the Earth and try to actually look for evidence of past life on the planet. So with the 2020 rover mission, we're actually going to really make a step towards the future in terms of understanding what the history of life is like on the planet. Now, this is a colorful and somewhat complicated drawing that I just want to point out a couple of things. This is where the 2020 rover can land. There's a black line here and a black line here. We can land between those black lines. The black shaded areas that you see are too high. The gray shaded areas, there's too much dust. And so it really turns out that in terms of the terrain on Mars, there's really not a lot that we can go to in terms of area. But what's interesting is we're lucky that these areas hold what we see from orbit, what we've seen from our rovers, we think are some fundamental clues about whether or not there was ever life on Mars. So we can take advantage of where we can go and, I think, make 2020 a big success in terms of understanding whether there was life on the planet. Now, the final slide I'll show you here is a different version of that previous slide. Again, we can't go down here, we can't go up here, we're sort of limited between. The little red flags that you see are the final 8 candidate landing sites for the 2020 mission. One of the things that I do with a colleague out at the Jet Propulsion Lab is lead the community process in terms of proposing and evaluating landing sites for these missions. And the 8 finalists that you see here really represent quite a diversity. There's some interesting choices. The Columbia Hills and Gusev Crater, in fact, we've been there. But a couple of things that we've seen there in terms of the rocks and their types are very compelling. We might want to go back with the different instruments and see if there's evidence of past life. Some of the places, Eberswalde and Holden, Northeast Syrtis, and some of these other places, we've heard before in previous landing site discussions. We didn't go there with Curiosity or with Spirit or Opportunity, but we were very interested in them. And in this case, with different sets of instruments, one of these might rise to the top. So if you go and you look at these different sites, and you can do that because there's a website up there called Mars Next, you can kind of dig into the details of why these are very interesting places and why we think that this is a set of 8, one of which will be selected as the landing site for the 2020 rover. Okay, so with that, I will stop and see if you folks have any questions for me about either what's been going on Mars or what's going to happen on Mars in the future.
Actually, we have an online question.
Okay.
We can get the online question. Well, I thought we had an online question, but if anyone has a question, please line up and we'll take them here. I have a question for you.
Sure.
How do you choose the names of the landing sites?
Well, the names of the landing sites are chosen for place names on Mars. So that part of it's easy, but when we land and we name a rock this or that, it's done differently on different missions. So for example, with Spirit and Opportunity, it changed with the seasons. Home plate, which I talked about with the Spirit rover, and a place that we negotiated around with Spirit, is actually something that we named at a portion in the mission, at a time in the mission when it was around spring training, and we were looking back at old baseball players and baseball fields and things like that. In the case of Gale Crater with the Curiosity rover, We mapped the surface of the planet before we landed, and we mapped those based on places that we see here on the Earth. And so when we see rocks in those locations, we actually pick names that correspond to those places. Yes, sir.
You've seen that there were habitability conditions on Mars. What's your intelligent guess whether there was life on Mars or not, or whether there is life on Mars?
It's evolving. So the question is whether or not I think there was ever life on Mars based on everything we've seen today. And I won't give you a hard answer because I don't know the answer yet. My sense is, though, I'm definitely heading towards there certainly could have been. When I started in this game, which seems a long time ago to me now, the idea that there was water running on the surface was something we understood, but it was a little bit abstract. And now that we've been down on the surface and seen the details and seen how everywhere we've gone with spirit, opportunity, with curiosity, there's rocks that were related to past water and conditions that might have been habitable. As we see more and more of those, to me, it tells of a place that in the first billion or so years of the planet's history was very different than it is today. That's, again, not to say that it was just awash in water and life, but there was water ponding in lakes, and conditions were certainly there. So I'm definitely headed down the road that life was possible.
Have you discovered whether there are any of the 4 elements that we need for life on Earth?
Yes.
Like
Yes, we
niacin?
see those.
You have all of those?
Yeah, we see a range of elements. Nothing in that set of materials that we see excludes the possibility of life.
Thank you.
And actually, we got our online question.
Okay.
up. How do you actually drive the rover? Is there a steering wheel?
How do we actually drive the rover, or is there a steering wheel? Well, when I'm involved in operations, I actually do it from right here in the museum. I have a different role in the 2 rovers. On one, I actually lead the day-to-day planning on the days that I'm scheduled. And on the other, it's more thinking ahead about what we're going to do in the next days to coming weeks. But when we do this, we do it with the engineers out of the Jet Propulsion Lab. And there is no steering wheel. It's all planned in a very careful sequence of computer commands. And we take a day's worth of commands and uplink those to the spacecraft all at a time. The spacecraft goes through its sequences and then sends back data. Part of the reason why there's no steering wheel is there's a lot of distance between the Earth and Mars. And it turns out that that distance is so great that the delay in terms of light traveling from the Earth to Mars can be minutes to as much as, say, close to 20 minutes, approaching 18 minutes or something like that. And so if you were driving something along the surface and you didn't know where you were going until 8 minutes after you got there, or 10 minutes or 15 minutes, you might have driven off a cliff or into a crater or something like that. So no, we don't use a steering wheel, and we use very carefully sequenced computer commands to send up to the rover to tell it exactly what to do and where to go.
My name is Tanisha, and I go to Whittier Education Campus. My question is, what were they specifically looking for on Mars?
Well, ultimately, we want to understand whether or not there was life there. The question was, what are we ultimately looking for on Mars? We want to know if there was life there. That's sort of the goal of people like myself. But there's a bigger sort of question and objective. Eventually, we want humans to go there too. And so somewhere down the road, perhaps in your lifetime, I hope, we will not be talking about rovers on the surface of Mars. We'll be talking about explorers, human explorers on the surface. We want to understand whether the Earth is unique not only in the solar system, but also in our universe in terms of harboring life. And Mars, because we see all these conditions that are reminiscent of the kind of environments on the Earth where we see life, because Mars is the next planet out from the sun from us, and that makes it somewhat more accessible, it becomes a very good target for trying to understand whether we're alone or not, and it also becomes a very good target for eventual human exploration.
Thank you.
My name is Tamaya from Whittier EC, and my question is the black hole closer to the outer planets or the inner planet?
I'm sorry, is the
Black hole closer to the outer planets?
the black hole?
Yeah,
Planet.
black holes.
Okay, so there's black holes, but that's not related to the story of Mars and the kinds of things that we've been talking about. In our own solar system, there's the sun and then the planets further out. There are black holes around our galaxy and in the center of a number of different galaxies, but we don't have one here that's sort of closer to or further from any of our planets within the solar system.
My name is Derek. I'm from Whittier Education Campus. I know that we're talking about getting humans and probes onto Mars, but research says that it's impossible to live on Mars because of the climate in Mars.
Okay, so the climate, you're right. The question is, I think, it's really not a very hospitable place today. Mars has a very thin atmosphere. It's very cold. It's not the kind of place where if you were there, you could kind of throw open the door and walk outside. You would need a spacesuit. You would need to be in a sort of environmentally controlled situation. A very popular movie, The Martian, kind of portrayed some of those sorts of conditions. In fact, Mars, because it's smaller, has lost a lot of its atmosphere, and it's cooled off more quickly than the Earth because it lost its heat more quickly. And so that tells us, based on the evidence that I've been describing, that it was very different in the past than the conditions that you rightfully describe today is not very hospitable. And so the answers to the questions we want to get out are, what was it like 3.5, 4 billion years ago? And why, if it was like that then, did it change to get to what it's like today?
One more question. I know you're a geologist, right?
Yes.
Is there a more habitable climate that you have found on Mars?
Well, I would say that in terms of the long-lived conditions, long-lived by hundreds to thousands of years, that we see in Gale Crater, and the fact that we see those with clays, tell us that the water that was there for a long time was actually occurring in a form, in an environment that is very similar in terms of sort of neutral conditions that are habitable. And so for me, when I look at Meridiani Planum and I look at the carbonates in Gusev Crater, those represent past habitable conditions or potentially habitable conditions on Mars. But when I look at these ancient lake beds in Gale Crater, I think, to me, there's very little question that that represents a past environment that was habitable. Now, whether there was life there or not is a very different question. But certainly the conditions, based on what we know about conditions here on the Earth, could have allowed it. Yes, sir.
My name is Davion, and I wanted to know, how long have rovers been searching for life on Mars?
Well, how long have rovers been searching for life on Mars? The Opportunity rover has been plugging along since 2004. But there was a rover on Mars before that, the Sojourner rover, associated with the Pathfinder mission back in the late 1990s. It didn't go as far away from where it landed as the rovers that we've been talking about, and it was much smaller, so it couldn't hold as many instruments. So really, when you thought about that whole sequence of missions that I showed you in a slide, it's not just the rovers, it's also the things in orbit around Mars that collectively build up the kind of information we need to understand Mars, how it evolved, and whether or not there was life. But in terms of actually rovers rolling around on the surface, with respect to Pathfinders, we're approaching almost 20 years. Now, Pathfinder hasn't been working for a number of years. Opportunity's been working now for well over its lifetime, but discontinuously we've had rovers for nearly that long.
My name is Tanisha, and I'm from Whittier EC. And my question is, will other countries help you build the new probe, or y'all gotta build it yourselves?
Well, my personal opinion is that we want to have other countries help us, because one of the things that allows is a lot of different viewpoints in terms of how we should accomplish things, but it also allows you to pool your resources. So if I want to buy something in the store and I don't have enough money, but my sister's got half of what I need and I got the other half, I say, hey, Sue, that's my sister's name, let's get together, pool our resources, and we can buy this thing. If NASA, in my opinion, works with other countries and everybody contributes some, then we can get to the kinds of missions that I think we need to answer these big questions about whether there was life on Mars and so on. So to me, this sort of cooperation with other countries is a very valuable thing.
My name is Marcus, and I want to know how long does it take a rover to get to Mars?
That's a good question, because oftentimes, for example, with Spirit and Opportunity, by the time you launched to when it got to Mars, it went almost 110 million miles, I think. It takes a long time to go that far. It takes months. So in the case of Spirit and Opportunity, they were launched in June of 2003, and they didn't land until January of 2004. So there's a very long period of time where they're crossing that distance in space after they left the Earth before they get to Mars.
We're going to have to break for NASA TV, but John, can you hang out a
Yes,
bit
I can.
and answer some more of these questions?
I'd be happy to.
Okay, great. Thank you.
Okay. Okay. Well, thank you all for coming. I appreciate your attention. I hope you learned something about Mars and found it interesting. I'd like to thank the sponsor of What's New in Aerospace, Boeing Corporation, and I appreciate your time and attention.
And just give us a minute, and then he'll answer whatever question. I think it's after.